Today we're going to talk about a topic that you definitely covered in grade 10 if you took applied. If anyone took academic, do they actually? I don't know if they actually cover this in 10 academic. Anyway, in 10 applied they definitely do. So we'll go through it, but it starts with this, which is pretty straightforward stuff. But we have two different words for these situations where these two shapes we say are, what's this word? Congruent. All right. Stupid word, but there you go. And we say these two are
not the same.
Yeah, we say they're not the same, but they are similar. So my question is, first of all, what does the word congruent mean? It's math speak, but what's it mean?
It's the same measurement.
Yeah, and it wouldn't even have to be tilted. I mean, if I drew those and neither of them was tilted, they would still be congruent. When we talk about shapes, one of the things we want to talk about is you can always rotate them and it doesn't change anything. In other words, if I take this and I rotate it like this, if I changed its shape, is it a different shape?
Oh.
No, now if I did this, is it a different shape? Yes, that bent a lot more than I was expecting it to. Wow. So that is changing its shape, but just rotating it does not change its shape. Does that make sense? So these two tortoises, they are the exact same shape. So exactly the same shape, we call that congruent. But what does it mean that these two things are similar?
Same shape, just larger.
Yeah, larger. Or if we were talking about this one, we would say it's the same shape, but smaller. So in just day-to-day life, that works as a definition, I guess. Same shape, but larger or smaller? Yeah, I think that works. It's not a very mathy definition, which I like, I think. It uses, like, English, which I support. So with that in mind, all of these are, if they were congruent, they would have to be the same size. Is that congruent? Similar, good. Hey, if I measured these angles, what do you think I would find? Like if I measured that angle and that angle, they should be, I'm not looking for the number, but just what do you think I'd see? You're probably right, but they should definitely be, the same. And if I measured this angle up here, it should be the same. Because remember, if the shape is the same, the angles should all stay the same. Right? And so if I measure this angle, it should be the same as that angle. Does that make sense? What about these two? They've been kind of twisted, but they're similar. And again, if I measure this angle, what does that line up with on the other one? Can you see it? Good. What about this one? Like this one here? No? Oh, whoa. Okay, good. What if I did this one? Where would that be? Like down here? Yeah, I agree. Does that make sense? So we can maybe add to our definition. The angles should stay the same. Oh boy. So if the shape is the same, then the angles have to be the same. Does that make sense? You can scale it up, you can make it bigger, you can scale it down and make it smaller. But if it's similar, we have to have not changed the angles. All right. What I'd like you to do is use a ruler and just a ruler. And by the way, I made it a right angle triangle, so it'd be nice and easy for you, because right angles are pretty easy to make, right? If you have a phone, you can get a right angle. I want you to take this triangle and make a triangle that is similar to it. triangle that is similar to it. It's a great idea, but I want real numbers. Yeah, so I want it, yeah, use your ruler. I want it to be really, 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 really precise. By the way, once you measure the numbers, what could you do to make sure you get similar numbers? Should we subtract or add? Yeah, which one do you think it is? Subtract or add or multiply and divide? I think you're right. Oh, I wonder if I could show that. I'm going to measure mine. Now, because mine isn't printed on paper, I'm probably going to get different numbers from you, which I didn't really think about, but whatever. We'll make it work. I guess I could do this. Okay, that's pretty close. Because it's going to get. Oh. It's not 5.8, that's 4.8. Okay, so Sam had the she wobbled a bit, which is great. Like we said, if you're going to make it similar, what could you do with the numbers? And at first she said you could like add or subtract all of them. And then she said, oh, you could divide or multiply. So I thought I'd do both and see which one works. So here I subtracted 2 from every side. And what do I get? What do you notice about this one? It doesn't work, right? They won't fit. They won't connect. Whereas when I divided them all by 2, it connects. It makes a triangle. Does that make sense? So that was actually, I hadn't planned to show it that way, but that actually makes a lot of sense. So we can actually kind of make a rule from this, which is we could say the angles have to be the same. But how do you get the new sides? They all have to be. But what did you do? Like, how long did you make all your new sides?
I mean, 1 centimeter, 2 inches.
Okay.
Mine's 5, 5.9.
How did you get those from the original? Or did you just try to eyeball something that looked the same? Okay, if you wanted to get exact, and that's okay, we can definitely do that. If you wanted to get exact, what would you have to do with the numbers? You could take all those numbers and you could divide them by all the same number. If we'd wanted to make it bigger, what could we have done? Multiplied. If I wanted to make the same triangle but 3 times bigger, what would I do with all the sides? Multiply them by 3. If I wanted to take the same triangle but make it 6 times smaller, what would I do with all the numbers? Very good. So to make 2 figures similar, the angles have to be the same, and the sides have to be divided or multiplied by the same number. That makes sense. That every once in a while is making sense. So I want you to look at these, and I want to say something. These drawings are intentionally screwed up as drawings, and that's not a mistake. All right? I want you to look at the numbers to see if you can tell from one of the 2 rules if they're similar. So don't look at the drawings because I have intentionally kind of screwed the drawings up, okay? In other words, if you measure these, is that actually 15 and that actually 21? No. So I want you to look at the numbers, not at the drawings, and see if you can tell me, are these similar or are they not similar? And they come in pairs, right? Like I'm talking about these 2 as a pair, these 2 as a pair, these 2 as a pair, and those 2 as a pair. Are they similar or are they not dissimilar? I don't know. And while you do that, I'm going to do my attendance. I did almost forget. And I'm going to stop screen sharing while I do that.
Huh?
Again, you can't measure. The drawings are intentionally screwbally. You have to look at the numbers. Because, yeah, the drawings, they suck. They're not right. Give me 2 seconds. I'm just going to get my attendance put in so I don't get yelled at. Daisy is here. Tyler is here. Dawson is here. Yes, I'm trying to be better this semester. Kendra is here. Michaela is here. Hunter is here. That's Hope, right? I got it. It's in the vault. That's it. Yep. You got it. Yep. All the inside angles add up to 180. Yeah. All right. We are back. Okay, what do you say? These ones are not. Why do you say that?
I'm trying to look at like the size and it didn't seem like they like kind of lined up.
Yeah, because what have they done to this one? One you get to two, they've made it twice as big, right? They've made it twice as big.
You are rid of it.
This, but it's really, no, and this twice as big as each one, but it's this one. I'm not going to see. I know they look really good.
But then they look like the same.
Well, what's the good? What do they have to add up to? See what you need for approval here, see what you need for approval. The one that says 10 becomes, that might help them. 5 becomes, yeah, take a look at this. I'm not sure that. We call it. It's similar because it's double. Double means double. It's similar because that's got to be good. That double. But that doesn't. Good. Well done. This is the sneaky one. Right
Down lined up.
Pretty good. Here, that angle is between these two sides. Right? Here, that angle is. Right here, it's between the 7 and 5. So it's not between 7 and 5. Yeah. It's a little sneaky. So these could be similar, but we don't know for sure. Right? It could be that these two angles are the same, which means they would be. But if they're different, then they're not. Does that make sense? That's the sneaky one. That's the one that's.
Well, then I figured it out.
Yeah. Well done. Exactly right. Good. Very good. Would I be rushing anyone if we started looking at this together, or do you want to map more? I'm going to take your stony silence to mean I'm good. All right. Oh, I hate having to sit down for this. And I'm not going to stop whining about it either, if you're wondering. So, what can you tell me about this top one? First of all, do you think it's similar or not? But second of all, how did you think about it? What did you do to get that decision made? What did you do? Okay, so so this side to this side, they're obviously the same side. And what did we do to that number? We doubled it, right? And so then this side to that side, what did we do? Doubled it. And this side to that side, we doubled it. And since all the sides have been multiplied by the same number, that was one of our two definitions, right? We said the sides divided or multiplied by the same number means they must be similar. So yeah, that is similar. Good. I like that. What about this one over here? What do we think? Well, what does this side line up with? One unit lines up with, which one on here do you think that matches up with? 2. Good. And how do we get from there to there? Like, how do you make 1 into 2 by multiplying? What did you have to multiply it by? Yeah, by specifically? Good. We multiplied this one by 2. So what should we have to multiply this one by? We have to multiply them all by the same number, which would give us 4. But what is it? 5. And when we multiply this one by 2, what should it give us? 6. But what did it give us? So this one is not similar. Good. Because of that, and because of that, we're going to say this is And that's a tricky one, for sure, right? Because they're close. But some of you were tricked, which is good. That means I'm doing my job. Some of you weren't, which means I need to try harder. What about this one down here? Again, the angles are not drawn accurately necessarily. I'm not claiming they are, but I see different angles. So my instinct is to say not similar. Because here I have 59 and 40, and here I have 59 and 81, right? Different angles. So because the angles are different, I am going to say not similar. Am I right? I'm getting a head shake from a disappointed looking head shake saying Orlando. Stupid, stupid Orlando. Why not, Ms. Stern? Ah, there's a missing angle. How would I find this angle? Good. So the whole thing has to add up to 180. And if that's true, then this little angle here should be 180 minus 81 and minus 59, right? And when we do that, 180 minus 81 is 99. Minus 59 should be 40. Anyone, is that what we get? I'm not making a stupid mistake. Ah, and just for the sake of argument, if the whole thing has to be 180, how would I get this angle here? 180 minus 40 minus 59. 180 minus 59 is 131, is 121. And that minus 40 is 81, I think. And so now what do we know about these two triangles? Yeah, they're similar because they have the same angles, right? If you look, this 81 lines up with that 81. This 40 lines up with that 40. And this 59 lines up with that 59. They've just been rotated, right? If you took this whole one here and rotated it that way, you'd get it lined up with that one. Does that make sense? That's a sneaky one. But not as sneaky as the most sneaky one. What do we notice about the sides here? How did we get from 5 to 15? What did we multiply by? 3. Okay, so we multiplied that one by 3. And from 7 to 21, what did we do? Ah, so those both work. The problem is, do we know if the third side works? Did I give you any numbers? No, I didn't. Now, I did give you angles, and I said this angle is the same as this angle. But what should this angle be the same as? What angle should that match up with? This angle here is between the two sides we know. On the bigger triangle, where is that angle? Between the two sides we know. Right? Where the two sides we know meet. That's where we have this one on here. And where is it on this one? Yeah, that should be this angle. Now, is it possible that those two angles are the same in both triangles and these are similar? It's possible, but do we know that? So this one, you just have to say not sure. I'm not sure if the angles are the same because I don't know all three angles. I'm not sure if all three sides have been multiplied by the same thing because I don't know all three sides. Does that make sense? I'm just not sure. It could be. It may be the same. It may be different. We don't know. So sometimes that's the answer. That's an okay answer. Do you mind? Put that down for me. Thank you. I can't do two things at once. I can barely do one thing at once. Okay. Now, all of which is to say this. In about the next 5 minutes or so, we're going to remind ourselves how to solve these, and then you're going to do a few questions, and then we'll probably do that. Nice and easy ones. But yesterday we talked about ratios, right? And today we're talking about similar triangles. Is there a connection between similar triangles and ratios? Spoiler alert, since I'm asking the question, the answer is obviously yes. Very good. You guys are good. On time? You could be great. So the question is this. We said that triangles are similar if all three sides are multiplied by the same number, right? Or divided, but we're going to stick with multiplying because that's easier to think about. So here's what I want to say. When we look at any triangle like this, we can say, okay, these two triangles are similar because I'm told they're similar. All right? We could do the division and figure it out, but I'm just going to tell you right now, these are similar. Well, if they are similar, then by definition, we've said all the sides must have been multiplied by the same number, right? That's the definition of similar. If we take all the sides on this small triangle, there's a number we could multiply them all by to get the big number. Does that make sense? So to do that, we're going to make a ratio. Actually, we're going to make 3. Why 3? That's an interesting number. Why would I make 3 ratio? Very good. How many sides does a triangle have? 3. If I was doing this with rectangles, how many ratios would I make? If I was working with hexagons, how many ratios would I make? Hex is, that's octa, that's deca. Very good, 6. 6 is hexa. What about a nonagon? Yeah, it is. Very good. So that'd be 9. But anyway, we're not dealing with nonagons, nor hexagons, nor decagons, nor dodecagons, nor octagons, nor I'm out of ones that I know. But we could call Calford here, and I bet he could go for days saying different gons. But we're dealing with triangles, and triangles have 3 sides. So we are going to make how many ratios? 3. So here's a rule I'm going to say. Multiplying by big numbers is nice, and multiplying by decimals is kind of weird, right? So here's going to be our rule. When we make the ratio, we're going to put the big triangle on top, always. Put the big triangle on top when we make our ratios. And what we're going to say is this. We're going to find sides that match up with one another. So on the big triangle, pick a side. Doesn't matter which one you pick. Okay, perfect. So we're going to pick this side BC, and we say that one lines up with, good. And we're just going to set that up as a ratio. We're going to say that we could take side BC and divide it by the length of ED, and that would be a ratio. That makes sense? But I want to introduce you to something new. And if you've already written that, it's okay, sorry. Which is in this class, and this is something we didn't do in grade 10, there's a little bit of a rule for how we name our triangles, which is it gets cumbersome to always write sides as 2 letters. So instead, we're just going to write the sides as 1 letter. And we're not going to do the opposite, hypotenuse or adjacent, because this isn't a right angle triangle, so it doesn't have a hypotenuse. So here's the problem. This side touches angle B, and it touches angle C. What's the only angle it doesn't touch? A. So we're just going to name it little a. We always use lowercase letters for sides, and we always name it based on the angle it's across from. Does that make sense? So we're going to say this one is side A. What then would be the name of this side from E to D down here? What are we going to call it? Yeah, very good. We would call this side F because it's across from the angle F. It doesn't touch angle F. Is that okay? Does that feel a little weird? Do you want me to explain that again, or are we good? So we would say that A lines up with F. Before we keep going, let's name all the sides. What would the name of this side be? Very good. It'd be side little c. And what about this one here? Very good. And again, all lowercase. When we do trigonometry from now on, we're only ever going to use 1-letter names, and the sides are always lowercase, and the angles are always uppercase. Maybe you want to make a note about that. Sides, lowercase name. Angles, uppercase. And let's look then at this little triangle down here. We said this one was side F. What would this 5.7 be called? Yeah, very good. And 2.4? Very good. Well done. Does that make sense? Is that comfortable? You'll find that if it's a little weird at first, it's a lot nicer than constantly writing AB over BC, all that jazz, right? So we said that side A lines up with side F. Who can tell me the next pair that line up? Good. So side B lines up with side E. And I can put that here. And I'm saying these ratios are equal because remember, the definition of similar triangles is these have all been multiplied by the same number. So the ratios have to be the same. If A was twice as big as F, then B would have to be twice as big as E because all these sides are multiplied by the same number. And obviously, if we've got two of them, what's the last pair? C and D. And again, I always put the big triangle on top. There's nothing magical about that. The math works if you put the big triangle on the bottom, but you'll get nicer numbers this way. And if you just give yourself a rule that you always follow, you're less likely to screw up. Does that make sense? So if we just say, hey, always put the big triangle on top, that's easy. Now, if I wanted to actually know what this ratio is, I could put the numbers in here. What is A? 13.9. What is F? Very good. What is B? Very good. Yeah, here we're not solving for anything, right? Here we're just setting it up. On the next page, we're going to solve for an unknown side. You're totally right. But if B is 12.4, what's E? 5.7. And the last, do you find it chilly? I could turn the heat up a bit. I'll turn the heat up a bit. You might like that. Should I turn it down even more? Get you the day off? Is this like how I like spill things on the ground intentionally before I go into the lab? And I think maybe today I'll slip. Hasn't happened yet, but I just keep trying. One of these days, I'm like, week off. Paid week off. Okay, and how big is C? 5.3. And how big is D? Cool. And you can test these. If you do this division, you should get the same number for each. Now, to be clear, because we're dealing with decimals, will they be a little bit different because these numbers are rounded? Yeah, they're going to be a little different. But these should all give you the same decimal number, which is what? Has someone actually done this? I will do it. $13.9 divided by 6.4 gives us 2.17. 12.4 divided by 5.7 gives us 2.17. And 5.3 divided by 2.4, this is probably going to be a little wonky, 2.2, right? And if you round these to one decimal, they all equal 2.2, right? Again, they aren't perfect because I've only given you one decimal place. If you measured all these to 5 decimal places, you'd get really, really accurate numbers. If you measured these all to 100 decimal places, you'd get really, really, really accurate numbers. Because these are only to one decimal place, this number will be accurate to one decimal place. And if you look, 2.2, 2.2, 2.2. So we get the same ratio. Does that make sense? All right, I want you to try the same thing with these ones. So I want you to name all of the sides, set the fractions up, and then find the scale factor. And I should say here,
how does this school not have enough calculators? I'm getting tired of telling coming in here and calculators for class. Look at this was colored on. Are you from this class too?
Probably not. That's from my class last.
Could be Orlando's class.
Actually, last semester I had pretty tame classes. They were lovely. I've got a good run of classes at the scale. The first, can you name all the sides? Just like, so let's call this side C. How did I get that back? Yeah, you call this one B. You did the same thing. Nice. Yeah, just use lower cases. We use uppercase letters for the angles and lowercase for the side. Okay, and it's then this one. Okay, now, and see how above we now said which side goes to which side? We'll do the same thing here. You have to make three fractions. And again, why are there three fractions? The triangles have four. Yeah. Now the actual scale factor we get just by doing that division. Right? So you use this calculation. And it doesn't matter which pair you pick, because they should all give you the same thing. Right? See how here I used all three and they all equal 2.2? You don't have to do all three. You pick one, divide it. And since this has one decimal place, how many decimal places are you going to put in your answer? Yeah. How we do it? Straight up violet. Okay. No, okay. So where are we at? What I want you to do is help me take this from what we're going to put here. Okay. Still good. You don't need to panic. There it is. All right. So I want you to first explain to me how you name the sides. Okay. You comfortable with that? So what I'm going to do first. Yeah, of course. That's what you got. That's great. And now the actual scale factor, remember, we got by actually doing the division. And you can pick any one of your three ratios, and it should give you the answer. And the only last thing I'll say is, how many decimal places are we using? 1. So how many decimal places should your scale factor go to? Yeah. Bingo. Can I see? Did you get a number? Alex. Fantastic. Awesome. Yeah, that was great. Yeah, well done. That's great. Well done. Fantastic. And actually set the scale factor. Just actually do that division. Any one of those. No matter which one you do. No, what? Sorry. Oh, I'm sorry. I'm doing one that you asked me to do. No, you're good. You're good. Just make sure when we take it up, make sure you come back and you got the same thing. Does anyone mind if I get going, or do you want to make more? Sorry? More time? Okay, so I'll give you a minute. We got a lot of it. We got nothing but time. But... Oh, that's that's lots of time.
Sorry, guys. I just want. I'm not I don't know.
Explaining well. Yeah, just explaining you when you need it. Guys, you open one. Okay, if you're still plugging away, you can ignore me while I do this early bit. But Mr. Kerrigan, can I ask you, sir, how did you name the sides of this first triangle?
You look.
Okay.
You're like, hey, 5.3 centimeters. You look. Oh my God, C does not touch it.
So that one is going to be called C.
C.
Perfect. Oh, never mind. You're good.
A isn't touching the nice little 3.1 centimeters, so you stick an A there.
Great.
And then same thing for 7.0 for D. It's not touching it.
Very good. Thank you very much. Maddie, do you want to tell me how you named the small one? Yeah. Very good. Excellent. Very good. Thank you. All right. So is everyone comfortable with those as the names of those? If you have a question about that, don't be shy. Now's the time to ask. By the way, about that, I just want to set a rule up. Nobody's going to screw up in this class more than I am. Don't be shy about dumb questions. I'm not going to be one of these teachers who says, like, there's no such thing as a dumb question. Yeah, no, there are. That's okay. But listen, even if you ask a dumb question, I'm going to say 50 dumb things a day. It's fine. If you don't know something, just ask. Sorry? Did I?
There's an M that has an extra little half of it.
Those are cursive.
Yeah.
Do you guys not learn cursive?
Not at
C,
all.
D, E.
I'm trying to teach in grade 4, then they gave up
Sorry.
after like a week.
I think it's not.
How's that? Does anyone still watch The Simpsons? I love The Simpsons.
They predict everything.
Anyway, there's a great episode of The Simpsons where Bart gets sent to gifted by mistake. So he switches names on a test with Martin, the smart kid in class. And so he gets sent to gifted class. And the teacher says, do you know cursive? And he goes, well, I know damn and hell. And then she cuts him off. And he thinks that cursive means swearing. Anyway, that's the end of my story. Okay, what do we do now that we've named the sides? What did you do next? You put them together. So give me a pairing. Yeah, give me one of them. A lines up with O. And so I could come over here and I could say A and O are a pair. I could even go below and put the numbers on that if I felt like it. What is the number for A? Great. Thank you. Noah, can you give me another pair?
What, sorry?
Can you give me another pair? We're on the you try one. So I've already done A lines up with O. So if you have another pair for me.
C lines up with them.
Very good.
5.33.6.
Perfect. So C lines up with M. Oh, that's not where I meant to put that. C lines up with M, and that means 5.3 lines up with 3.6. Shh, gentlemen. And Hunter, can you give me the last pair? Yeah, please. So I've got A and C. Yep. Very good. So B lines up with N. And what numbers are that?
7.
Very good. And listen, it's important to make sure all of these on the top should come from the same triangle. Does that make sense? The most common mistake, the thing most of you will do wrong, is you will do this at some point. All right? Where just by slip, just by making a mistake, but then if you look, do these come from the same triangle? They do not. All right? So we always put the numbers from the large triangle on top and the numbers from the small triangle on the bottom. And again, there's nothing magical about that. The math works just as well if you put the small one on top and the big one on the bottom. But if you set a rule for yourself, it's easy to follow, right? There's nothing magical about driving on the right side of the road. So why do we say that's a rule? Because if everyone does it, nobody gets into a collision. Does that make sense? I spent the summer in Haiti. Well, I didn't spend the whole summer in Haiti. I spent about 2 weeks, almost 3 weeks of the summer in Haiti. My wife's a midwife. She delivers babies for a living. And I talk about math for a living and can multiply numbers in my head. So we went to Haiti. I spent 2 weeks at a school teaching English, specifically medical English, to Haitians. But my wife spent 2.5 weeks teaching local Haitian women who are in a 1-year program to be midwives. So in Haiti, 85% of women during the course of their pregnancy will never see a doctor or a nurse or a midwife or any skilled attendant. And to give you a sense of scale, in Canada, 6 women out of every 100,000 will die of something childbirth related in their lives, which is too high, by the way. There's countries as low as 1 or 2, and Canada should be doing better than that. And the biggest problem in Canada is in our native populations and our northern populations that don't have good access to medical care. If you look at down here in southern Ontario, those numbers are about 0. So those communities that we really aren't serving well. But to give you a contrast, in Haiti, a woman has a 1 in 89 chance of dying in childbirth in her lifetime, which is unbelievable. So that means if you imagine the women in this school, in your graduating class, you can imagine that 1 or 2. It's just a staggering number. So it's a really backward system. It's got real problems. I mention this because this number's all on the top thing. When you get to Haiti, in our country, everyone drives on the right side of the road. And in Haiti, everyone drives wherever the hell they want to. And they go however fast they want to. And it is terrifying, absolutely terrifying. And the only way to get around really for the most part is you rent a motorcycle. And like you don't get to drive it. Like you pay a guy and he drives you around on a motorcycle. And Haitians are really homophobic. So like you dare not like touch the guy driving the motorcycle. So you just kind of sit at the back of the motorcycle and try not to fall off while they like drive around people carrying chickens and things like that. And it's starkly terrifying. So we all drive on the right side of the road because if everyone does the same thing, nobody screws up and it works, right? We always put the big number on the top of these ratios because if everyone does the same thing, nobody screws up. Listen, I'm telling a story here.
I really.
Yes.
So when you start solving for size, right?
Yep.
On the other page, is it like more beneficial because it gives you an automatic? It'll give you two, like it'll give you one automatically from the bigger triangle.
Yep.
And it'll give you one side automatically from the other triangle.
Yep.
You want to plug those into the middle so you can do it across multiple.
That's what we're going to show today. Yeah. That's not the only way to do it. There are other ways. So you could get the right answer doing it a different way, but that's what I'm going to teach today. Yes. Yeah, exactly. And what was the actual scale factor here? It shouldn't matter which one you pick. It is 1.4. So if you take that top number and divide it by the bottom number, you get 1.4, and that's true whichever pair you pick. Because in similar triangles, all the sides are multiplied by the same number. Now we can use this to solve. Wow, did you just print screwbally like this, or did you just print nicely? Oh, I don't know what happened here, but that's okay. Oh, I'm so sad. What are these numbers? This is 6.5. This is y. What is this number down here? I can't read it. 1.9. Okay, so we'll do this one together, and then you'll have time to maybe have time. Probably not. And we'll pick up when we get back tomorrow. But for this side, if we're going to name all these sides, what would I call this one? Yeah, that's fine. This would be side B. This would be side, and this would be side. Good. And over here, this Y would be called side F. 6.5 would be side. Very good. And 1.9 would be side. Excellent. Now I've twisted these around, but you're clever folk, right? You're folk who are clever. So this side C, what does it line up with? Good. So my first ratio, I could write that C and D make a pair. And I could even go down here and put the numbers in. Do I know C? For C, I'm putting what? Yeah, I don't know it, so it's X. Do I know D? Yeah, it's 1.9. That's the worst looking X anyone has ever drawn in the history of math. Yeah, it's fancy. I don't know. I always try to make sure it doesn't look like a multiplication sign. Who can give me the next pair? Andrew, do you have a pair? You're artsy, and I know this. So look, this side B here, is it more like F or is it more like E from this triangle over here? Well, E is the longest side in this triangle, right? And over here, so it lines up with? Nice. Shh, gentlemen. Gentlemen. Thank you. So on the top here would go B, and that lines up with F. And the last pair is Obviously the leftovers. I think you do. I think A lines up with E. Here's the deal. You won't lose marks if you get it right. If you make a mistake and I don't have work to show for you, then I can't give you marks for what I don't see, right? Does that make sense? But if you get it right, no, that's fine. Like, do I now show this every time? No. But it's a good thing to do when you're starting out, just to make sure you don't make a mistake. Now here, I have 3 fractions I want to solve, but I have to deal with one at a time, right? So we're just going to pick a ratio. So for now, which pair do you want to do first? I would say just focus on this first, right? And if I have 9.5 over y equals 11.3 over 6.5, how do I solve for that? We just cross multiply. So y would be equal to what? Okay, but yes. How do I get it?
9.5 times 6.5.
Very good. And that gives us 5.4. Great. Is that okay for everyone? You feel comfortable with that? And so now I can actually come up to this fraction if I want, and I can actually replace that with like 5.4. And if I know that that's 5.4, what can I do next? What can I do next? So now if I want to find x, what's my new ratio? That's right. It's the exact same thing. X over 1.9 equals 9.5 over 5.4. And how would I actually cross multiply this one? It's a 9, I think. Yeah. Over. Cool. And what does that give us? That sounds right. Did everyone get the same? Cool. So tomorrow we're going to pick up with this and we're going to keep going. So today was just kind of about getting it in your notes for you. And then tomorrow we will actually take some time and practice it. Does that make sense? Okay, if you could do me a favor, in the two minutes that remain, if you do have a yellow calculator, please put it back on the set. By the way, guys, when you put the calculators back, can you look at me? Do me a favor. At the bottom of the calculator, there's like 2 little metal bits that are the charging ports. Can you make sure they line up with the charging ports in there? Otherwise, when I plug them in, they don't charge. And then they're not charged. And then I get nasty emails like, why aren't the calculators charged? And I don't have a good answer. It's just like, because they're not.